Hi, and welcome to the Design Day video for Project 25031, the Dual Output Recon Camera, sponsored by Elbit Systems of America. First, let's get introduced to the team. On the left, we have our software engineer, Lucas Dent. Next, we have myself, David Ramsair. I'm a mechanical engineer. Next, we have our systems engineer, Arjun Dalal. Our optical engineer, Olive Mayer. Abigail Doyle is our mechanical engineer. And finally, Stuart Nickel is our optical engineer. Okay, so what exactly are we trying to do? Elbit Systems of America has a need for a device that they can use in testing and assisting the development of various electro-optical devices. What that means for us is that we are trying to design a device that will both illuminate and capture video footage of a target in both visible and near-infrared spectrums of light.
The goal of the dual output Recon camera is to illuminate an object at a distance of 500 meters under low light conditions. We do this using two lasers, a visible laser with a wide full field of view and an NIR laser with a narrower full field of view. The dork allows the user to switch between these two laser modes and output the video feed onto a standard external display. The dual output Recon camera has two settings, a situational awareness setting with visible illumination and a wide 20-degree full field of view, as well as a detection setting with an IR illumination and a narrow 5-degree full field of view. The camera body itself should be handheld and can be mounted on a tripod, and it has a weight requirement of 8 pounds or less. The DORG has 5 subsystems: imaging, illumination, processing, mechanical, and power. It is powered by a 12-volt source, and it allows the user to change between NIR and visible modes using a worm gear, which is used to manipulate a flip mirror inside the DORG.
Now let's talk about the design of our system. Here you can see just a top-level overview identifying some of the major subassemblies and how they're related to each other within the system. We have our imaging subassembly, which basically handles how we're taking our light in and getting it to the sensor. We have our illumination subassembly, which is the lasers. Our processor boards, you can see on the left, has addition to the integral display, which will display the video feed. Our control includes the worm gear, which we will expand more on later. And finally, the support housing is what's pictured transparently for your viewing ease.
The camera assembly itself consists of two different brackets, an imaging bracket and an illumination bracket. In the housing, the imaging bracket is held on top of the illumination bracket, and these two channels are bore-sighted within 2 microradians of each other. The imaging bracket consists of 2 imaging channels for the respective visible and near-infrared wavelengths in full field of views. We chose to use a single sensor for imaging, so we also employ a rotating mirror to allow the near-infrared light to be reflected into the sensor when the user is in the detection setting. The illumination bracket uses 2 separate diodes at wavelengths of 520 nanometers and 852 nanometers that are then sent through a beam expander so that the light is able to fill the 1 meter target at 500 meters away.
So here's our electrical wiring diagram. As you can see, everything is routed through the processor centrally. It powers all of our optical components and outputs the display. And it takes input from a couple analog switches. Unfortunately, our project did not get an electrical engineer, so we had some issues throughout the whole development process with powering the lasers, but we ultimately settled on a solution that implements a custom breadboard with some buck and boost converters to control the voltage. The processor is a Latte Panda 3 Delta microcomputer. We chose it because it was the best at the price point. It's versatile. It has Windows compatibility, which is necessary for the camera, and GPIO pins, which is necessary for the analog switches. The connection to the camera is done through FTDI, and the video is processed through OpenCV. The camera did originally come with software, but that software was suboptimal for our purposes, so we reprogrammed it, and it works much better now.
Pictured here is our control assembly. Using a worm gear, it allows the user to flip a mirror and switch between the visible and NIR settings. The optical mechanical system underwent multiple design changes before the final configuration you see here, in order to fit optical, electrical, and budget requirements.
An isolated look at the design of the support assembly. This is a very important component because it allows for each subassembly and component in the system to become precisely aligned with each other as well as be mounted in place. Now this is a fully custom design and fully 3D printed two-piece housing shroud.
This is a brief overview of the major system requirements the system satisfies. Our product is capable of dual camera imaging and illumination, has handheld portability, and an easy-to-use operating interface. The following images were taken from our testing space to confirm the workability of our DORC design. Both the visible and near-infrared optical channels image according to their optical specifications and image in a low-light environment. Both the visible and NIR channels can be toggled between using a mechanical dial and worm gear as previously mentioned. The following video highlights our visible illumination capabilities in our DORC system, as well as our integrated display and external display functionality. As seen in the video, our visible imaging channel can detect a 532 nanometer laser's output beam and display it on our two interfaces. The same applies for our near-infrared illumination capabilities. Despite being invisible to the human eye, our camera detects and images the corresponding NIR laser beam emitted from our NIR beam expander system.
Our final deliverables include the DORC system, the tripod stand, and the retroreflective target, as well as any CAD files from SolidWorks and source code, as well as the final report, software readmes, and an operating or a user manual.
The following operating conditions must be adhered to for a safe working environment. Our laser diodes have a power output of 50 milliwatts, and with our given specifications for beam expansion and use cases, the following safety measurements were taken. Our project utilizes Class 3 lasers, so it is imperative to abide by all safety precautions.
Conclusion. Using the needs given to us by Elbit Systems of America, our team designed, integrated, tested, developed, and produced a prototype device that can both illuminate, image, and process a target at the desired range for use in their field testing. Some of the lessons that we learned mostly relate to scheduling and how you need to really be ahead of schedule in order to be prepared for all of the inconsistencies, mistakes, and errors that will come up throughout the integration and testing process.
We would like to thank our sponsors Matthias Whitney and Jeremy Jackson from Elbit Systems of America for their help structuring this project and providing us with additional resources. We'd also like to thank our mentor Jim Sweetman for guiding us through these 2 semesters of senior design and enriching our learning experience. And finally, a special thanks to Dr. John Koschel, Dr. Jose Saucian, Hilary Mathis, and the College of Optical Sciences for their mentorship, design help, and testing resources.